one thing that is not really implied in the statement of the question, but something we're going to take advantage of, is the symmetry of the problem. If you were to figure out what's going on between these three anchor points in the ceiling there, you'll see that they form an equilateral triangle. And because they form an equilateral triangle, and that block is just hanging at rest below, that's going to force the cables all to have the same tension. So that kind of shortcuts the whole system thing at the end tremendously. And all the problems that we have with hanging with triple cables will be that way. If the pattern with the anchors was not an equilateral triangle, we would have to assume T1, T2, and T3 were different. But because it's an equilibrial triangle, we're going to assume the tensions are all the same. So this is the analogy to the cable problem where these angles right here are both the same. If those are both the same, you can assume that the left and the right force have the same magnitude. Whoops, I said right and wrote F. There we go, there we go. So you can assume that if those angles are the same, you can assume that the tensions or the forces in both are equal. So we're going to assume that. And this also, remember, the little vectors here, they have pointing towards the load. Quite frequently when we think about these problems, we think about those vectors as pointing away to offset the weight. So we just have to be careful with our signs. So the first thing we do is figure out our displacement vectors from the load up to our anchor point. And so we're just going to do a bunch of subtraction. And the way they've drawn the vectors, if we want to match what's in the picture, we should do load minus anchor point because of the way they have the vector pointing down. So we do the tip of the vector minus the tail of the vector. So we're going to start with 0, 0, negative 2 root 5, and we subtract off each of these to get, and that's not good math right there, point minus point, but you know what I mean, right? You know, we're creating a vector. So we're taking the load and subtracting off, so we're going to get 4, 0, and then minus 2 root 5. So that is a vector that's a displacement vector that is pointing from the anchor point over to the load. Saba just walked in, and who else just walked in? What is your first name?
Eric.
Eric. All right, so let's see. Oh, yes, gotcha. So that is that. One thing we're going to have to figure out is the length of that vector. So let's go ahead and do that. The length of that vector is going to be found by taking the square root of the sum of the squares. And that's going to be 16 plus 20 square root of 36, so we get a length of 6. Now what we can do is form the unit vector that points in this direction. So that's kind of what they're implying that little red vector is. It's a unit vector that points down towards the anchor. So that unit vector then is going to be equal to, I'm just going to call it U1. So that first unit vector is going to be the displacement vector divided by 6. So that will give us 2/3, that will give us 0, and that will give us minus the square root of 5 over 3. So that's the first one. Next one, we'll go with, let's see if we can do this a little bit more strategically instead of writing all that out. So our second one, let's take that minus that. So we're going to have 2. I have to do it the other way, though, because of the way they pointed. So 0 minus 2. So that's going to be negative 2. And then 0 minus 2 root 3. So that'll be 2 root 3. And then minus 2 root 5. And what's the length of this vector? Also 6. So this tells us that our second unit vector is going to be that vector divided by 6. So we're going to get negative 1/3. We're going to get root 3 over 3. And we're going to get minus 2 root 5 over 3. Any questions up to that point in finding that unit vector? Yeah.
How would it be different with the signs if it was load minus, or I'm sorry, anchors minus load, or?
So if we did anchor minus load, then we'd have the vectors pointing up.
Okay.
relative to the up direction. We have them pointing like that.
Isn't that what you have up there is anchor minus load?
This is load minus anchor. We're doing that minus, this is the load,
Okay, gotcha.
right? So that's the load minus the coordinates of the anchor point.
So would it be a sign change?
Yeah, it would be a sign. All it would do is change by a factor of -1.
And that would be that middle sign?
In that particular, so here all these would switch,
Okay,
and all those would switch.
okay,
So, well, I guess if we're looking at the unit vectors, those would both all change.
okay.
And then that third one, I think we did those two and those two, so we do those two, so it's going to be -2, and then -2 root 3, and then -2 root 5. And so then our third unit vector, so we're using this idea of scaling unit vectors. So what we've done is created 3 unit vectors that represent the direction down to the load, and now we're going to scale them by the tension that's in each anchor, or in each cable. Omar?
Wouldn't we lose both 2's on the 2 root 5's?
Oh, did I subtract incorrectly?
No, you divided incorrectly. You forgot to take out the 2's.
Over here,
Yeah, so on the
So when I-
Z.
when I
points-
divide by 6,
6,
that 2's gone.
Yes, sir.
Thank you very much. Trying to talk and think at the same time. Talk and think. It's not easy. It's what you guys are here for.
Do you have to get rid of it on the?
Did we not do it on that one either? Oh, that one also, thanks, yes. Yeah, great. Good division. Excellent division. Better to catch it now than later, right?
It's not the calculus, it's hard.
It's never the calc that's hard, it's always the arithmetic, as we know. Especially when you're talking. Okay, so everybody clear? We've got 3 unit vectors pointing from anchor points down to load. We don't know what the tension is, but we're assuming by symmetry that the tension in each cable is the same. So what we do then is the following. We're going to scale each one of these unit vectors by the tension. So we're going to say U1, that's the unit vector pointing down. We're going to call the tension there T. If the tensions weren't the same, we would call this T1. But we're assuming the tensions are the same. So this is by symmetry that we're allowed to do this. And now normally what we would do when you have equilibrium is that you do left plus right plus load equals 0. Right? But the load is negative, so you add it to the other side and it becomes positive. This one is different because the little vectors are pointing in the same direction as the load. Right? So we're not going to have that situation. This will be equal to not negative load, but actually equal to the load, which was, what was it, 0, 0, negative 500 or something?
Yeah.
Yeah.
So whatever that load is. Okay? So that's the one difference with this geometric setup than what I would intuitively do. I would have done it slightly differently, but it's fine. So now we have 3 equations here. Right? There's going to be the x component, the x component, and the x component added together to equal 0. Y component, y component, y component added to 0. Those are going to give you no information. Those are going to be like this problem where the horizontal forces cancel out and that doesn't give you any information about the vertical components. So the only component that's going to contribute anything will be the third component, third component, third component, third component not being 0. That's the one that's going to be the equation that's going to give us everything we need. So t times, let's look up here. So third component, we're going to have negative square root of 5 over 3 times t plus third component there is negative 5, negative root 5 over 3 times t. Third component there, oh, they're all the same, aren't they? Times t equals negative 500. And then we do what we have to do here. We add all these together. We divide out the minus. If we divide out the minus, we get a 500. When we add these together, what do we end up with? Just root 5t. So this tells us that the tension is going to be 500 divided by root 5, and then we'll rationalize it by multiplying top and bottom by square root of 5. We'll get 100 root 5. Okay, so that's the tension. And then the last thing, and this is where your question was, Brandon, now we would take that scaling factor, multiply it by each of the 3 unit vectors, and that will give us the vector representation of the force for each cable. That make sense?
Can you do that for one of them?
Say that once again.
For one of them, could you do that?
Yes. So if we look up here, we're going to take that unit vector and we're going to multiply it by that number. So that unit vector, what's that, 100 root 5? So we're going to take 100 root 5 and multiply it by that, that, and that. So let's do it in a different color up here. So that, this one, that I don't know what I want to call that. I'm not going to call it any name because we didn't name it yet. But if we multiply it by 100 root 5, we're going to have 200 root 5 over 3, 0, and then what, minus 500 over 3, I believe. So whichever cable that corresponded to, that's going to be the vector that represents the force or the in that cable. Grant?
Should that not be like 1500 over the square root of 5?
I don't know. Down below?
Yeah, because shouldn't you have to multiply both sides by 3 to get rid of that 3 on the bottom and the left? And then divide by
But
square
when
root
we
of 5?
add 1/3 plus 1/3 plus 1/3, we get 3/3.
Oh, okay, gotcha.
When we add these together, right, the thirds cancel out with the fact that there's 3 terms added together.
Okay.
That makes sense? And so then we would do that for the other 2 also to get the vector representation of the force for each cable. All right, so there's our, that's. All right, other questions from the 11.3 homework or other stuff that you might have got hung up on? Or should we start 11.4? Yeah. Ready to jump to 11.4 already? All right, so I think of what was, now the homework for 11.3 was actually pretty, there was a navigation thing in there too, right? Wasn't there the navigation problems at the end of 11.3? Let me just glance real quick at 11.3 and make sure that I don't want to, maybe we should at least mention navigation. Oh no, these were.
Yeah, they were, it was only 6 of them.
Yeah, there's only 6 questions. Yeah, this didn't have the navigation. This was all the projection.
Yeah.
Work.
I have a question about number 6 at the very, very, very end of the problem.
Okay. Hang on one sec.
Okay.
We'll get to that. I want to do one more question with the projection because this is so important and you're going to use it a lot. It's used a lot in physics. It's such an important concept that I want to make sure that we've got that type of problem down. So I'm going to do, before we start 11.4, let's go and do at least one more of these. So let's just create a problem on the fly. Let's suppose that we have, we're going to take 2 points in 3-dimensional space, and we're going to, let me just read that question again. How did they do it? Oh, they started with 2 vectors. Okay, so they weren't creating, okay. So we're going to start with 2 vectors in 3-dimensional space. This book always uses U and V. So we're going to start with U and V. 2 vectors with 3 components. And the question is going to be find P. And recall that P, by definition in this class, is the projection of U onto V. So we want to find that, and we also are going to want to find the scalar component of that, which we'll talk about that when we get down to it. Let's do this first, though. So find P. So P is this projection. So the formula we're going to use in here is U dot V. So that's where we start out. And we're projecting onto V. And so projecting onto V means that V is going to be the quantity that shows up in those other three positions in that formula. So whatever vector you're projecting onto is the one that's in the denominator. And the whole idea there is that the V dot V is closely related to the length of V. So V divided by the length of V. So it's good, that kind of gives you a clue that it should have V's in it because you're projecting onto V. And when you project onto a vector, you're basically scaling a unit vector. So once you've got the formula down, you've got to come up with ways to remember that formula, whether you're thinking about projecting onto V, so you need a unit vector in the V direction, which is V over length V. Somehow you've got to get that formula down because you use it a ton. So simple enough, once you have it down, U dot V, we multiply the corresponding components and add. So just a reminder, I'll just write it out like that so that it's hopefully a clue that that's what we're doing. Multiplying corresponding components and adds. Anyone have a question on that? So we're just jumping across. There's not many simpler math formulas than that one. If they all were that simple, we'd be psyched. All right, so then V dot V, we go through and we're multiplying the vector V's components by themselves. So we're basically squaring each component. So we're going to have 9 plus 4 plus 1. So that's the fractional part. That's a constant. That's a scalar. This whole thing here is just a scalar. That's the scalar that we're looking at right there. And then we have to scale vector V. Bless you. So there's vector V. So we're going to scale that. And this will give us our projection vector P. So, whoa.
It's
Zero.
Zero. What? What? You've got to be kidding me.
Did you mean
Zero.
to do that?
So what does that mean?
Everything's zero.
No, everything is not zero. You sound like such a nihilist. Everything is not zero. What does it mean?
Yeah, the zero vector. Yeah, you just have to write the little vector symbol.
Oh, good point. Good point. This is a vector. This is not a scalar. Good point. So it is a vector. But what does it mean about the original vectors?
They're orthogonal?
Yeah, U and V are orthogonal because the dot product is zero. Well, yeah, that. Oh, yeah, I guess because of the 2 and the 0. Yeah, okay. So let's make a little tweak because, okay, well, let's do one more then because that didn't really help us get to what I was hoping to get to. That was not very illustrative of what we're trying to do, but I'll be more careful this time. As soon as there's a 0, I need to be very careful. All right, so those two vectors are not orthogonal. That dot product is not 0. All right, so P will be the dot product, which is going to be 0 plus 1 minus 8. And the denominator is going to be 9 plus 1 plus 16. And then we're going to scale vector V. And so our projection vector is going to end up being minus 7 divided by 26 multiplied by that. Yeah, I went overboard. Now the numbers are nasty. All right, so we get negative 21 over 26. Negative 7 over 26, and positive 28 over 26, which is 14/13. So that's our projection vector. And anytime we're dealing with projection vectors, the image in your mind, regardless of whether we're in 2 space or 3 space or more space, we are thinking about this type of picture. I guess I'll have our black markers. So this projection vector is right there. That's vector P.
Sort of like the shadow you would cast.
The perpendicular
you would cast at-
shadow. Yep.
Yeah,
Exactly.
High noon.
Yep. That's right. The noon shadow. The noon shadow. All right. So, ooh, thank you. Where'd that come from? Oh, on that board over there, or did you pull it out of your pocket?
I have it. That one's mine.
Who walks around with markers? Dry erase markers. Bless you.
When you have a bunch of study groups,
You
carry
just bring
them.
markers just in case. So then P perpendicular. When we look at this picture up here, the idea between P and P perpendicular, sometimes this book calls it W. The idea is that the sum is going to give us back vector u. So we're decomposing u into these two perpendicular vectors or orthogonal vectors that add up to u. So if we're trying to find a component representation of P perp, we just subtract P from u. So we're going to come back over here, and we're going to take our original vector u, which was 0, 1, 2, and we're going to subtract off this P vector, and that will give us P perp. So subtract those two, and we get 26 over 26 plus 7, so that's 33 over 26. And then our last component, 26 minus 14 is 12 over 13, I believe. So that's our P perpendicular vector. So P plus P perp will give us U. And what is the geometric significance?
Question.
Yeah, go for it.
You just subtracted a unit vector from your first point, so didn't you just theoretically just move a unit vector?
Wait.
from
Which
one-
one's a unit vector?
0, 1, or sorry, the one on the right there, 21, negative 21 over 26, negative 7 over 26.
That's a unit vector?
No.
I beg to differ.
Oh, never mind, my bad.
No, it's fine. Yeah, so that's not a unit vector in general. It could be if it was a coincidence. So it could be, so the way we would form a unit vector for this here, we'd have to divide it by its length. But we're dividing by a sort of a random dot product type of scalar.
Yeah, sorry, I just misread it.
Oh, that's fine.
Yeah.
It's good. Yeah, so that's, everyone agree that's not a unit vector? And you would check in your mind if you squared, and added, it would not add up to 1. So that would be another thing. Yeah, Haley?
So you're subtracting vectors, right?
Yes.
So is it tail, or I'm sorry, tip minus, no, it's tail minus tip?
So up here, so we did u minus p, so we're doing u minus p, so.
But on the picture, what would the,
So the difference, that is p perp, it's right here.
right,
So that's also another representation of p perp. You could move it right over to there.
it's parallel transporting.
Parallel transporting. Yes.
It's like one of my favorite things.
One of your favorite things to do?
One of my favorite things to say.
Oh, parallel transport. Yes. So if we parallel transport down to the bottom of the slide here, what is the geometric significance for the length of p perp?
Distance?
The height is
Distance, height, yep, it's measuring this distance right here. So it's measuring the distance from whatever the tip of this vector, whatever the order triple is right there, which we don't know right now, that wasn't given to us. We don't know, but it's giving us that height right there, that distance between the tip of U and that line. That goes through V. That's what it would give us. And to find, let's not even find it though, that's a little too much. That's not what we need right now. That's not what we need.
It's 1,600, the square root of 1,674 over 1,521.
All right, we need it. So the length of P perp, tell me it again, Grant.
The square root of the fraction 1,674 over 1,521.
Gosh.
Sorry, no, the fraction is inside the square root.
I know. As soon as you said that, I started realizing. So square root of 1,674
And 74 over 1,521.
There we go. And then you can rationalize that if you want. Okay, but the significance is distance. Yeah.
Did you do the scalar projection? And I missed it? Like, is that part of this?
That's what we did. So,
Okay.
well, it depends on what you mean by that. This is the projection vector.
Okay.
And if your question is, what is the scalar component of u in the direction of v? Let's get there.
Oh, okay, we're not there.
Yeah, let's do that. So
I don't
the
even
scalar, and there's no shortcut word for this. So this looks almost identical to what we had above, that formula. We start with the dot product, but then in the denominator there is just the length of v. So that is the scalar component in the direction of v. Oh, I wrote this backwards though. Scalar component of u in the direction of v. The way they write it is with the u up here and the v down here, because we're projecting onto v. So I should have that down here and this up there. Why is that? This should be a reminder from a couple days ago. So if we take a look at the geometry here, if we think about the picture that is being made by this projection scenario right there, we're projecting down, we're forming this vector. And so just recall, and this is super helpful to think about, there's v. And then there's a unit vector that points in this direction here. That's going to be v divided by the length of v. And then vector p, is that one the red one? I can't tell. That's not the red one. The vector p is right there. So we think of p as a scalar multiple multiplied by the unit vector right there. And so what we ended up with was the following formula originally. We said that p was equal to u dot, that should have a vector symbol over it, u dot v divided by the length of v. No, I'm going to remember this now. Almost there. There was a v with no thing, and then this. So this is where we started out. That's where we started out a couple days ago, whenever it was, last week. So this here is a unit vector, and then we're scaling this unit vector by that scalar. And then the way we came up with this was by using the definition of the dot product. That got us all the way over there. So the important thing for you, there's two important things. That formula right there, and down here, if there was ever a question about just the magnitude of that vector and you weren't looking for the component form of p, you just wanted the magnitude of it, maybe I should say more than the magnitude, because this could be negative. So if you had an obtuse angle, that's when that scalar projection can be negative, if that dot product's negative. If it's acute, then that value will always be the length of p. So if the question just says find the magnitude of p, you can just do this, and that will get you to it quickly. So what was our dot product up there? Our dot product ended up being
0, 1, 8.
Right there. The dot product is just that, yeah. So -7, and then we divide by the length of v. And the length of v, I don't think did we ever find that exactly? I don't think we had to.
It's 6.
It's 6?
Should be.
6? Okay. Trust you. So -7 over.
Sorry, 26. 26.
26.
Square root of 26. Square root of 26.
Square root of it. Times 3. So the length of v is that. So if we go back up to v, just so everyone's clear, to find this would be 9 plus 1 plus 16, so square root of 26. Oh yeah, we did find that down here, right? So that is the scalar component of u in the direction of v. All that means is that that's how long p is if this was a positive number, and it means the opposite of the length if that was a negative, if it's a negative number.
Yeah, so that red equation for vector p, pretty much what we did here is kind of divide out the vector v's the same way we would in algebra.
Yeah, we went back, we used that dot product formula, and then we figured out the way we actually wrote it completely. The very first time we wrote it was like this. We wrote it as cosine of theta times the length of u, I believe. I think that's how we originally wrote it. Because when we project this vector down, right, that's going to be the magnitude of u. If we think about this right triangle here, So the magnitude of u is the hypotenuse of that right triangle. Magnitude of u times cosine of theta, and then we multiply it by that unit vector. So that's where it comes from originally. Yeah.
So, okay, so you're just saying, so that this is negative, so that just means that it's obtuse.
Obtuse. So
That's
the
all that is,
projection.
So that's still the length of P.
It's -1 times the length of p. Length has to be positive.
But it's still like if you were to take the absolute value.
Yes.
Okay.
Yes. Yes. So the magnitude of that is the length of p.
Okay.
Yeah. It's just that it's pointing that way instead of in the same
Okay.
direction as u. Yeah. So if you wanted to find the length of p, you would just take the absolute value of that. Yeah. Good. All right. Do you guys want to try one of those yourself?
Sure.
All right, let's have you try one, and then we'll jump into. So try this one. Suppose that you.
Don't make it 0.
Yeah. Beware the zero product. Beware.
There's one in the homework that's very like
Yeah.
It is, it wants you to
There's
find
one
it.
that's 0.
like
Yeah,
instant
they want you to
zero
find it.
or
All right,
something.
that one. Yeah, let's just say find p. Well, I'll say find p and p perp. Find p and p perp. Find p and p perp. That scalar component thing, we aren't going to use that for these in these problems at all. So I won't ask you to find that. You know, trying to remember another formula is not useful. If you know how to find the projection vector and the question says how long is the projection vector, find the projection vector and take its length. You know, trying to remember another formula just for the length of the vector is not helpful. So don't bother. Because there's lots of problems where you have to find p anyway. So if you have to find p anyway, find its length after you find it. Yes, so it's multiply that. Yeah, square add. Yeah, you're off and rolling. Yes, that's only to find that scale. Yeah.
No, it's just what's
Yeah, we again.
Yeah,
we
it
could
just
use
wants us
that.
to do this what we did before.
99%
just
you
do
want to know what
the
P
That
is
one
like.
and then do minus that one.
Minus
Okay. Okay.
That's it.
5.
What'd you get?
Oh, I'm trying to do algebra in my head still.
I feel you.
I'm trying not to use my
That's the start
calculator
of the beginning of it.
so much. So I'm just gonna sit and look
No,
at
it's
it.
supposed to be a
Okay.
box.
So -2.
Yeah.
5 halves.
I did put a little squiggle there though, so that would have been long division.
Yeah, exactly. Dividing.
Oh, it's a half. Okay. Half.
2 plus 0 plus 3. Dot product.
Oh, 2.
1 plus 0 plus 1. Any issues with
My algebra.
this part here?
1/2, 1/6.
That all look good
1/2, 1/6.
conceptually? So we, excuse me? We end up with 5 halves
Subtracting.
multiplied by that
Oh, we got very different answers.
minus 5 halves.
Oh, you know what? I wrote 1 there instead of 5 halves. 5 halves times 1 is not 1.
Everybody good with that projection vector? Yeah.
Just a quick question.
Sure.
So, I guess
then
you can
this
see it,
one.
my picture here. So when you find our projection vector,
Subtracting
this
this
is u
and this is
onto
bigger.
vector v,
Okay.
which gives us this projection vector.
Okay,
Do you
yeah,
also
1/2,
theoretically
1/2,
just set up a
1/2.
problem like
Yes.
this, do like
Yeah.
And then you just do that by
Okay.
subtracting.
Sorry, so
Rather-
that's
That's
Like for two
So that's
vectors,
P per.
theoretically just do
Okay.
something like
Not that. I feel like it's.
Yeah.
because there was, I don't know, is that a way to do
That would do.
I know,
That would
it
work.
seems like it should
Except
be
that you're
longer.
gonna accept that the only issue
We
is,
just
this is a
understand
true
it.
statement, but the solutions to this aren't gonna be unique. Because there's gonna be an infinite number of vectors that are perpendicular to space. So then you'd have to do, you'd have to somehow use some additional condition to narrow it down.
translate it?
Yeah.
Okay.
So it's true that P dot P perp will always give you 0, but trying to use that as the means to get P perp is gonna be ambiguous.
Gotcha, that makes
One
sense.
half, one half.
All right, and then P perp,
You.
P perp is gonna be the original vector U, wherever it is, -2, 1, 3. And we subtract off that vector. And if you can subtract correctly with fractions, you probably got it right. So we have 2 plus 2.5, that's 4.5. And then 1 minus 0.
Wait, why is it
Negative.
What?
Oh, I can't subtract properly with fractions.
Okay. I was like, but
Negative. So it should just be a positive 1/2.
Okay, good. Good.
Oh man, it's fractions. And then 3, so then 3, okay, then this one is also 1/2.
Yes.
Yes.
All right, okay,
Good.
good.
All right.
All right, we're there.
Oh gosh.
You
We
will
made it.
have what we wrote on our paper.
We made it.
You will get to this.
Subtracting. And if we can subtract correctly, we get the right answer. Subtracting, always a challenge. All right, anyone have a question on any step up there? So, as long as you get that formula down, you should be good.
One U, 4 V's.
1U, 4 V's. Yep, 1U, 4 V's. UV, VV, V.
Or if we were doing U, it would just be UV, UU, U.
You got it right.
You know it.
Right.
Yes, what you said. All right, cross products. So I mentioned this last week, right? We've only had 1 week of class, so okay, I'm not lying, right? It was last week. We have two types of multiplication. You can either multiply 2 vectors with the dot product or with the cross product. And what we've seen with the dot product is a scalar valued function. If you take 2 vectors and you dot them together, you get a number as the result, a scalar. So we call that a scalar valued function. And then the cross product, a little different. When we take 2 vectors and we cross them, we are going to get a third vector. This is something that we're going to refer to as a vector valued function because the output is another vector. So it's a vector valued function. The value of the function is a vector. Will?
Oh yeah, so it looks very similar to the dot product, except yeah, U times V is an absolute bars
Yep.
thing right there, and
Magnitude.
also instead of cosine
Sine.
angle, it's sine angle.
Right, that's exactly right. So it's almost identical. So dot product, when you look at the definition, you get length of U, length of V times cosine theta. For the third vector, the first thing I want to mention is that it's going to be perpendicular to the 2 that you're crossing. So if the black vector here is U, and that's V, when you go from U to V, if you cross U with V, you're going to get a vector that points in that direction of your thumb. All right? If you crossed U cross V, if you went the other direction, you're going to end up with a vector that points down. So you have to use the right-hand rule when you're going from the first vector to the second vector. So if I do red cross black here, it's going to point down, but if I do black cross red, it points up. Okay, so I put it that way. If I do black cross red, it's pointing out that way, but if I do red cross black, it's pointing into the board. So we use the right-hand rule. So whenever we do the right-hand rule for vector cross producting, you start your fingers at the first vector and you curl to the second, and your thumb points in the direction of the cross product vector. So that tells us something really important. The cross product of 2 vectors is not commutative. U cross V is not the same as V cross U. So it's your first experience with a non-commutative type of multiplication. So I think that's on the next slide. Okay, so that's the geometry of the cross product. It's a vector that points perpendicular to the 2 vectors you start with. And then here's our formula that relates the magnitude of the cross product. So the magnitude of the cross product is going to be the length of u times the length of v times the sine of theta. So very close to the dot product, sine instead of cosine. And the dot product, you don't put an absolute value around it. The dot product is already a scalar, right, by itself. U dot v is a number. U cross v is a vector. So on the right side, we have a number, because it's a number times a number times a number. So to make this left-hand side a number, we have to take the length of u cross v, take the magnitude of it. OK, so let's take a look at the geometric significance of the cross product. So A, the first piece of the geometry is that it's pointing perpendicular to the two component vectors, the two vectors that we started with. But check this out. So if we imagine u and v sharing this initial point right there, do you see that the area of this parallelogram is going to be equal to the cross product's magnitude? Can you see that? So the area of a parallelogram is the length of the base, which is magnitude of u, multiplied by the height. Well, the height of this vector, the height right there between this vector and this vector down there, the height of that is length of the red vector, length of v times the sine of theta. So the area of this parallelogram is that times that, which we just defined to be the magnitude of the cross product. So the magnitude of the cross product is going to give us the area of this parallelogram. And that, usually in math, these definitions, we define things in a way that has geometric significance. So it's not that they defined this first and then realized the area of the parallelogram happened to be the magnitude of the cross product. It's the other way around. Playing with this the triangle or parallelogram there, it's like, oh, wait, look, the area of this is what it is. Let's back up and let's define the cross product to be such that it's going to give us this geometric conclusion. You have a question, Will?
Yeah, so, yeah, look, you say that take the cross product of u and v and it's orthogonal, so, or orthogonal to both, so the resulting will point upward.
Up or down, depending on...
Is it possible to take a cross product of two vectors with only two components?
No.
No? Okay. Has to be
Cross
three.
product is only defined when you have vectors with 3 components.
Right.
Not 4, not 2.
All right.
So it's unique to 3-dimensional space. So if you're in 2-dimensional space, you could trick it, and you could say you could add a 0 to each of the 2 vectors, and then you could cross them. But the cross product is defined only for vectors with 3 components.
So the dot product will work with any vector, but cross product is for 3.
Yeah. Dot product works for any dimension. Cross product only 3. Yeah. So this is a nice geometric significance. The length of the cross product's the area of that parallelogram. If somebody said, hey, well, what's the area of this triangle that's formed by the vectors there? Well, we would take the length of the cross product, that's the parallelogram's area, divided by 2, and we get the area of the triangle that's formed by 2 vectors. So that's one nice thing. Another really cool application is that, isn't that P perp's length? Right? This gives us a really slick way to find the distance between a point and a line. Find the area of the corresponding parallelogram, area of parallelogram divided by the base of the parallelogram gives us the height of the parallelogram. So if we were given this vector here, u, we can find its length easily enough. We can find the area of the parallelogram easily enough. Area of parallelogram divided by length of base will give us height. So that's another way to find the distance between a point and a line in a more quick, in a way that's a lot quicker than using P perp. So that's Michael. Question. So a little bit weird though. That cross product vector is pointing perpendicular, and the length of that vector gives you the area of that parallelogram. All right. A little strange. Strange but true. So the question is, how do we mechanically evaluate the cross product of two vectors. So some of you, I'm sure, have not seen this. So let's talk about have you guys talked, has anyone not seen this? I feel like some people have definitely not seen this. Okay. So what we're going to do is this process, it's a lot simpler than it looks. Before I even go through the explanation of that, I'm going to take a look at this example and I'm going to try to parallel it so you can kind of see what I'm doing and I'll explain it. So when we want to find the cross product of this vector, of these two vectors, I've told you that the result is a third vector. So we have to end up with a vector in three-dimensional space. Up here in this formula, they're using I, J, and K. Those are representing the unit vectors that point in the, point in those directions. I in the X direction, J in the Y direction, K in the Z direction. So this is what we're going to do. We're going to set up this matrix, and when you have a matrix, and instead of using brackets, typically when you define a matrix, you use brackets. So notice that we have absolute value, an absolute value symbol instead of brackets. So that means the determinant of the matrix. Okay, so that symbol right there means determinant. Now, the way we evaluate it is with these minor matrices. So when you have a 3x3 matrix and you cross out a row and a column, you end up with something called a minor matrix. And that's what those three things are. They're called minor matrices. And what we're doing is then finding the so-called determinant of those. So let's write this out, and then we'll talk about what happens. So to get the first minor here, we cross out the first column, the first row, and we have 2, 0, negative 1, 1, multiplied by the unit vector I. Minus. Now, we'll talk about that minus in a second. Just follow the formula for now. So now to get the second minor, we cross out the first row and the second column and take the extra the four entries that remain. And that's multiplied by J. And then the last one, we get rid of top row, third column, and that's multiplied by K. So this is how you would definitely write it out if you were in a physics class. In a math class, I will write it out. That's how the book defines it, but a lot of us would just write it this way in a math class, where we automatically break this into, we know it's going to be a 3-component vector, so we just jump right to this. We don't deal with the I, J, and K. Either way is totally fine. Yeah?
Is that what you expect us to do then for this class?
Either way is totally fine. If you want to do it that way, it's fine. I'll show you what I expect you to do in 1 minute, because after you've done it this long way, like 3 times, you'll be able to write the answer down immediately without bothering with all these intermediate steps. So now, the big question. How do we evaluate a 2x2 determinant? We've seen that a 3x3 determinant is done in pieces with 2x2 determinants. To evaluate a 2x2 determinant, you take the main diagonals product is down to the right, and you subtract off the other diagonals product. So this is going to be main diagonals product is 2 minus the other diagonals product is 0. Over here we have a minus. Main diagonals product is negative 1. Other diagonals product is 0. Main diagonals product is 1. Other diagonals product is 6. So we end up all the way down to the point where we end up with a vector 2, 1, negative 5. So that will be the cross product vector. That is our cross product vector. One quick check that you're probably on the right track. is that if you take it and dot it with each of those, you better get 0. So if you dot it with this one, you have -2, +2, 0. That adds to 0. Dot it with this one, you get 6, -1, -5, that adds to 0. The chances of both of those being 0 and you having the wrong vector is very small. Question?
Where did the negative come from?
Yeah,
on
I'm about
the
to
j-
explain
okay.
that. Yeah, good question. Okay, so that's how you find the vector. You know how to find its length. So let me show you one more example, and then we'll talk about that negative thing. All right, so here's how you're going to get really comfortable doing it like this. If you write down this step, you will get to the point where you just do it all at once. And to get the x component, cross out first row, first column, you do -4 minus -3. So -4 plus 3, -1. The y component, cross out the middle column, you do 8 minus 0, you get 8, but then you reverse the sign and get -8. So the middle component always has a reverse sign. Third component, cross out the third column, -12 minus 0, you get -12. So you'll get to that point. I'll give you one so that you can see if you can do it quickly.
I can see the pattern when you cross out the middle row because your hands are in the way. Sorry. What's the pattern for the middle row? I'm just not seeing it.
So for the middle row or middle column?
Or sorry, middle column.
Yeah, you never cross out the middle row
Yeah.
when you're doing a cross product. When you're doing a 3x3 determinant in general, you could cross out a middle row. But for us, with a cross product, you always cross out the top row and then one of the columns. So when you cross out the middle column, 4 times 2 is 8,
Oh, gotcha.
minus 0, and then reverse the sign.
Okay, gotcha.
Okay, so let me put one up here for you to do, see if you can do it so that you don't have to spend all that. Actually, let's just write the whole kit and caboodle in this form already, just to practice the nuts and bolts of it. Oops, and I should have a row of IJK. Okay, so see if you can get this one. One thing that's helpful is to actually write the structure of your vector over there so you know that you've got a vector and you find I and then J and then K. Find each individual piece. See if you can do it in one without writing all the intermediate steps down. You'll have to remember that down to the right is the main diagonal. Down to the right.
I got a question.
Yeah.
I still remember from chemistry, so I don't forget everything.
Mhm.
My home.
Oh, you can do that with J. Yeah, yeah. I will say that eventually.
Okay.
Not yet.
Too soon, too soon.
Yeah. Yeah, that's absolutely true. First component, anyone? -3?
Yep.
Everyone agree? So we did the main diagonal minus the other diagonal. So main diagonal, and then subtract off the product down the other diagonal for that little minor. And then we go to J, cross that out. 2 minus 3 is -1. Switch the sign. K, cross out the third column. And, oh, that's the one I actually drew up here, right? K, we get -2 minus 6, so -8. Everyone agree with that?
So wait, just a quick question.
Yeah.
So we don't look at anything in I when we're solving for I, and it's -2 minus 1 then?
Yeah, so for the I component, it's that minus that. So
Okay.
it's negative 2 minus 1 gives us that one. And then for J, it's the 2 minus 3 is negative 1 and switch the
And
sign.
then we subtract this way.
Yeah.
Okay.
So, okay, one point that came up, let's take a look at J just a little bit more carefully. There is a second way to do J, and it depends on what you're most comfortable with. So with J, where you're dealing with those guys right there, you can just continue to do, if you're still very fuzzy on determinants, you always do main diagonal minus the other diagonal, and then if you're in the middle, you switch the sign. With J, if you wanted to, instead of doing main minus other, you could do other minus main and not worry about switching the sign. So with J, instead of doing main minus other and switching the sign, you could do 3 minus 2 and then not
You get
switch.
1.
Did I say that right?
Yeah.
Yeah. So 3 minus 2 is 1. So you could do it that way also. So if you want to just sort of remember one thing, main minus other, main minus other, main minus other, and then for J, switch it, that's totally fine. But as you start doing it more and more, you'll realize the pattern with J is that you could just do other minus main would also work. If you can keep that straight. Okay, so let's talk a little bit more about determinants. So this is kind of a modified determinant. When you get into linear algebra and you're doing determinants in general, so typically in linear algebra, you're going to have something like this. You're going to have a 3x3 matrix of numbers. And you're finding the determinant of that. The determinant of a matrix of numbers, first off, determinant is only defined if you have a square matrix. And you can do it for a 3x3, a 4x4, a 5x5, a 6x6, whatever. And you get into a programming class, it's very simple. You just hit DET parentheses, the matrix name. On any graphing calculator, same thing. If you go into the matrix area, you can enter your square matrix and then click determinant, and it will tell it to you. So the determinant has different geometric properties. We've talked a little bit about the cross product and its geometric significance with the area of the parallelogram. With a 3x3 determinant of numbers, if you imagine 3 vectors, so all with the same initial point, you can imagine extending those 3 vectors and building a parallel piped. So you extend in all those directions. You can build, just like 2 vectors will build a parallelogram. You've got 2 vectors like that. You're going to form an implied parallelogram. A set of 3 will form a parallel piped. And the cross product over here found the area of the parallelogram. You can do something over here that's going to give you a number that's representing the volume of the parallel piped. Okay, now how do you find that? We're not going to do a lot of this in this class. This is more of a linear algebra thing. But the idea is the generality of what we just did. Here you can pick a column or a row to expand around. It doesn't matter. For us, cross product, you have to expand around the top row. You have to do that. So watch this. It doesn't matter. I'm going to do 2 of these. There's a lot of them. You can pick any row or any column to expand about. Usually if there's a 0, that's the place to focus in on, is a column or a row with a 0. I won't do that though. I'm just going to grab this column. Instead of expanding around the top row like we just did, we're going to expand around that column. And here's what you would do. So these guys are going to act like multipliers, the -1, the 2, and the 4. They're going to act kind of like I had the I, J, and K up there originally. So they act like multipliers. The middle one is always going to be changed in sign because there's this so-called sign array. So embedded on a matrix is something that we refer to as the sign array. And that sign array is basically a +1 or a -1 that we use as a multiplier in conjunction with the determinant of this little minor matrix that we're creating when we cross out a row and a column. And so if you went to a 4x4, plus minus, whatever column or row you choose, those little minuses are just multiplied as a +1 or a -1 to affect the values. So right there, because of that sign array value, that's what gives us the negative there. And now, we chose to expand about column 3. So I put the -1 there. The minor matrix associated with -1 is right here. We do main minus others, that's 0 minus 3, that's -2. And then we go to the next entry, 2. The 4 entries left over after we cross out that column and that row that the 2 comes from, we have -1 minus 6, which is -5. The 4, we have 1 minus 0, which is 1. So this is going to be the value of the determinant. And that number is unique. It does not matter which column or row you expand about. So let's do one more just to rub it in that that is not going to matter. So this time, let's go around the middle column because there's 2 minuses. So let's see if we can figure out how that works. So when there's 2 minuses, there's going to be a minus and a minus there for the sign array. So let's see. We should get the same number. If we don't get the same number, it's a terrible definition. We better get the same number. So we're going to do -2 multiplied by, so we're going to, -2's right there. We look at the 4 entries that are not part of the column or row there. We cross out the column and row. So we get 0 minus 6. So we get -6. And then we go to the middle entry. That's a +1. Multiplied by the 4 entries that are left. That's 4 minus -3. That's 7. And then we go to the third one. We have -1, but we have to change the sign. So we're going to make it +1. And then we have 2 minus 0. And that should be 16. 12.
I think that the -2 up there
That one?
on the first one you did. I think that's supposed to be -3 because you're doing -1 and then you're doing 0 minus 3.
For this one right here, let me just double check up here. So I've got that one. I have -1 times 0 minus 3. Oh, yeah. Thank you. So right there. Right, we chose the -1, but then this area here, the main diagonal is 0 minus 3. 3 times 1 is -3. I did 3 minus 1. I did 1 minus 3 instead of multiplying it. Everybody see? Everybody see that right here? When we do the little determinant of a 2 by 2, it's this product minus this product. So we're subtracting off 3. And that should be -3. 0 minus 3 is -3. So this should be a +3. So this should be 17. Is that what we get down here? No. Not yet? What the heck? This really works. I promise. I promise. Did I write down the matrix correctly? I wrote it the same. All right, let me just go through it in my head real quick. Talking and doing algebra, arithmetic, at the same time. All right, so first off, let's see, -1, 0 minus 3. Second one is -2. And I have -1 minus 6. That's a problem. Right here. -2. That's -1 minus 6. -1 minus 6 is? -7. Oh, good grief. Okay, so that's +14 in the middle. +14. So now we're up to 21. 21. Now does it match?
Yeah.
Yes, now it matches. All right. All right. This is not something we do in this class.
So we're not going to be studying how to do this.
This is something you'll do in linear algebra, but the idea is that for cross products, we're taking this one application of a determinant and we're using it. And it's much easier with cross products because we always expand about row 1. But just showing you in general, you can expand around any row or any column, and if you do it carefully, you get the same answer. All right. Okay, so do you want to try another cross product? Oh, no, let's take a break. Let's take a break.
You want to try?
Resume. Cross product of unit vectors. This is pretty simple. The nice thing is that if you take 2 unit vectors and 2 of these standard unit vectors, I, J, or K, and you cross them, you're going to get one of the other ones, possibly multiplied by a -1. All you have to do is use the right-hand rule So if you use the right-hand rule, let's suppose this is I right here pointing out at you, J right there, K right there. If you go I cross J, you get K. If you went J cross I, you would get minus K. Right? I cross J is K. J cross I minus K. If you do, what if you do K cross I?
J.
K cross I is J. I cross K, negative J. Right? So with these, any of these unit vectors, it works out really nicely. You just have to follow the right-hand rule. And if you cross a vector with itself, we just saw a moment ago that we had this property that the magnitude of the cross product is equal to the length of u times the length of v times the sine of theta. So let's analyze this right here. So I cross I, we're getting 0. Does that make sense? So geometrically, we said that this is the area of the corresponding parallelogram. So if you have two vectors that don't coincide, or they're not parallel, let's say, you're going to have a parallelogram. So there's going to be area. But if you have two vectors that are pointing in the same direction, or pointing in opposite directions, I can't do that. Not that flexible. So two vectors like that or two vectors like that, is there a parallelogram formed? No. You have a degenerate parallelogram with 0 area. So you degenerate parallelogram, you get no area. So 0 is the cross product between two parallel vectors. So that gives you a fast way to determine whether two vectors are parallel or not. If their cross product is 0, they must be parallel, which means either they point in the same direction or they point in opposite directions. So similar to the dot product. Dot product, if it's 0, your vectors are orthogonal. So cross product and dot product give you some nice geometric testing. If the cross product is 0, they're parallel. If the dot product is 0, they're perpendicular. Okay, properties of the cross product. The only one that we really see that is important for most of our problem solving is that it's an anti-commutative property. U cross V and V cross U are not the same, point in opposite directions. The other properties kind of follow with other distributive and associative properties that you've seen with other types of combining of vectors. So associative property, constants can be pulled to the front and then you can cross U and V. You could distribute and cross U with V and U with W. You can distribute in either way. So both those distributive properties work. I wouldn't write those down. Those are just something you can reference if you need to look them up in the book. That one, though, is the most important one. That's the one we see the most, is that they are not commutative. So it's an anti-commutative operation. Anti-commutative. All right, let's do a couple applications. Find the area of the parallelogram formed by the following vectors. So the parallelogram, we said, has area equal to the length of the cross product. So that's pretty cool. So the area is going to be the length of U cross V. And the length of U cross V is the determinant that we represent with the following matrix. And that's going to be a vector with 3 components. The first component will be -8 plus 12. The second component will be -32 plus 6, which is -26, and then change the sign. Third component, 32 minus 4. So double check that all the arithmetic worked properly there. Double check. And I should still include absolute value bars around this because we haven't completely finished yet. Let me think about how I want to notate that. So the cross product is a vector. I'm not going to put this equal sign here. That equal sign I shouldn't put there yet. There shouldn't be an equal there because this symbol here, the determinant, that's representing a vector. And then we have one more step. Once we complete that and get the vector, now we have to find the length by doing square, 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 add. So 16 plus 26 squared plus 28 squared. And then we take the square root of that, which is probably not a perfect square. And what did they say? They didn't say anything. Let's just suppose if they said to round to the nearest tenth, we would get this. If they said to write it in exact form, we would get something like 2. Let's see, what's 14? I don't know. 2 root 369. That still doesn't look like it's all the way down. You know how to do that part though. Figure out the biggest perfect squares and pull them out.
So is that the area of the parallelogram?
So this is the approximate area right there, and it depends on. I didn't write down what the result should be. And here we have exact. Do we see another perfect square in there?
641. 6 square root of 41.
6 square root of 41 total.
Yep.
Thank you. 6 square root of 41. Okay, yeah, 9 did go into that last one. Yeah. So square root of 9 is 3, so we get 6 on the outside. Yeah, in the test I would say write the answer in exact form, or write the answer in approximate form rounded to 1 decimal place or 2 decimal places. Okay, so that is the area of the parallelogram. So nice application for the cross product. Let's talk about torque. It's kind of small print there, but so another application is finding torque, and the idea is pretty simple. If we imagine an arm, they call it like a lever arm. Think of it as a wrench or something. And then over here we have a bolt that we're turning. So that's a bolt. So we've got our wrench. Usually we call that vector R, some sort of radius vector coming off the bolt head. And then we're going to apply a force out here at the end of the wrench to either tighten or untighten the bolt. And this is called the force. And the angle that the force is applied at is right there. And bless you. And torque is a measure of the twisting force. So torque is a scalar, measures the twisting force, and it has units of Newton meters, but it is not work. So when you're dealing with work, you get Newton meters and you convert that into a joule. A Newton meter, when you're talking about rotational force, cannot be turned into a joule, and it is not work. So rotational force is totally different than other lateral force or whatever they're called. All right, so you're going to get Newton meters as your units, but you are not dealing with work. All right, so there's a weird, subtle distinction which you'll learn in some physics class, like Physics 5 or something.
Yeah, so pretty much work is for translation, torque is for rotation.
Yes.
Okay.
Yeah. Torque is a rotational force, magnitude of the rotational force. Yeah. Yeah, and there's some things with momentum and blah blah that I don't know physics too well. All right. So torque is going to be found by using this cross product. So we're going to find the length of the cross product of R cross F. And in practice, we are often in these types of applications given the angle, so we can convert this over to the length of R times the length of F times the sine of the angle in between. So that's going to be how we define torque. So R cross F. So in this particular case, if I go R cross F, cross product's going into the board, so we're tightening it. And what angle would give you maximum torque? 90 degrees. Right, because sine of theta has its largest value when theta is 90 degrees. Sine of theta fluctuates between -1 and 1, and its max value would be when theta is 90. So if we crank that direction, that's going to give us the maximum torque on that hole. Yeah.
So you said the torque was a scalar?
Torque is a scalar.
So how come you can just set it equal to the cross product? Because that'll yield a vector. Don't you
This
need
is
length
the
of vector?
absolute value of the cross product.
Oh, gotcha.
Right, so that guy right there, those two absolute value symbols mean, or that one absolute value symbol with two parts, that represents the length of the vector.
Okay.
Yeah, yeah. Yeah,
So that would mean you would get a vector and then you would do
magnitude.
square, square, square.
Yep.
Square root. Okay.
Yep. Unless we calculate it this way. If you calculate
Then
it
it's
this,
just
then you're just getting numbers multiplied together. So in this particular case, let's see if we can come up with our vectors that represent the R and the F. Let's see what they say. So suppose you apply a force of 20 newtons. So they've already told us, and torque, a lot of times they use a Greek letter tau to represent. So they tell us that the force is 20 newtons. So 20 newtons. 0.25 meter long wrench. So the length of the wrench, that's the magnitude of R, so that's only 1/4 of a meter, 1/4 of a meter. And they tell us that it's applied at an angle of 45 degrees, so sine of 45 degrees is √2/2. So our torque is going to be 5√2/2 Newton meters. That will be the torque. Yeah.
How did you do the right-hand thumb rule on this one? You said it went into the board?
So it's always R cross F with these, and so with the way we've drawn it here, that's going into the board.
What is that out of the board?
How do you
Is
mean
it
R-
going in the direction of R?
R
and then-
cross F. So we rotate from R over to F.
But aren't you curling up towards F? Because you're going in the direction of R.
No, you start from R and you roll your fingers towards F. So with your right hand. Oh, that's your right hand.
Yeah.
So why can't you
Like
just?
this?
Because the force
So-
vector for F is down.
Oh, it's going down on
So-
it,
yeah,
not
don't,
away from
yeah,
it.
don't follow that, that little arrow up there.
Okay.
Force is down.
Okay, cool.
Ooh, yeah,
Then
that.
that makes sense. All right.
So if it was like a
That's how
three,
you-
like
that's how I think of it.
three-dimensionally, I guess.
Well, if we're at 90 degrees right there,
You have to go.
it doesn't matter. So if you take those two, if I write those two vectors, it doesn't really matter if you just roll, this is vector R, this is vector F. You go from R over to F.
But how do you know where
I
that
think there's
is from?
confusion
Go
in the
full circle to
direction
get over
orientation of your thumb. Because you can hold your thumb like this and cross it goes in, but you can also hold your hand like this and cross towards it, it goes the other way.
If we're going from, you take your fingers from here over to there. If you're going from this vector to that vector, it's going out.
Well, aren't you supposed to stick your fingers in the direction of the first vector listed?
No.
No, you're not.
Are you
You're supposed to roll your fingers from the first vector to the second
So it
vector.
would technically be like.
It's like rolling a sushi roll.
So wait, how is that?
You have to make that sound.
You'll do this in practice in physics, where they'll give you like, so you roll your fingers from one to the other. So look, so if I start here and I roll that way, right? If I want to start over here and roll this way, it's going to come out of the board.
Okay, but for this, if you're like, by the way that you're using those two marks, I'm assuming you're saying if they both have the same starting point.
It does. You can put this wherever you want.
Yeah,
Okay.
and
Put
if
there.
you
Then you're
and
moving
go
F
this,
into
and
R.
they would be coming out of the
Then-
board.
Oh, I see what you mean. I
Yeah.
see. So you're talking about because. Okay, I got you. If you move it over here, this force is always applied to the tip of the wrench.
Okay, so that's enough to change the whole direction.
Yes. Because we just saw that it did, right? Because here we're rolling from R over towards F, but here R to F would be the other way.
Okay.
Yeah.
Yeah.
Okay.
When, yeah, that. So.
If you're crossing R into F, then it would start this way and go this way. But now it's.
Let me look it up. Doesn't matter if we don't care in this
Yeah.
class. They'll care like 2 hallways down, maybe. But for us, we always do R cross F. It doesn't matter if it's going in or the only difference is either you're tightening the bolt or you're untightening the bolt, and that's not a question we ask in math. Are you tightening the bolt or untightening the bolt?
And the difference is just a negative sign, so
And the difference is just a negative sign. And when you take the absolute value,
it's nothing.
it's insignificant. Yeah. Right, because torque is the magnitude of the cross product. So whether it's going in or going out, it doesn't matter because we just take the absolute value anyway. But that's a great question. I'll talk to one of those physics freaks down there and get a better idea. Oh, you're one of them, right? Grant?
I have a startling revelation.
Oh, good.
It says that it's tightening the bolt already.
Excellent.
You do that in math.
But what if it's reverse threaded?
Left-hand thread.
Like, how do you remember on your bicycle which way to tighten your pedal?
No, it's righty,
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 righty.
lefty.
Not in your pedals.
Oh.
Tightening is always forward and untightening is always backwards on your pedals.
Oh.
They're like pipes and the same
Wow.
thing.
What's that?
Are we
Pipes,
mechanics
same
now?
thing. Pipes are switched.
Switch, yes. There's a lot of things that are reverse threaded.
They put pipes.
So you
the
don't
other
take
way
your
so
pedals
when
off?
people get trapped inside, they can turn it off.
You leave them on?
Yeah.
All right, let's do another one of these.
Yes.
So pump handle, here they're pivoting, they decided that we're gonna use the origin as the pivot point and it extends out to a point. So that's our lever arm. So we're gonna call that R, and the component form of the vector that we are dealing with then is gonna be 5, 0, 5, 0, negative 5. So 5, 0, negative 5, because we're starting at the origin, we do our displacement, we get that the terminal point of the vector represents the same, has the same components. Okay, and then the force, they give it to us. Force is gonna be 1, 0, negative 10, and it's applied at P, which is the end of the lever arm. Find the magnitude and direction of the torque about the pivot. Okay.
Can we just do cross product?
So we do the cross product, so R cross F. And now here, we don't have the angle in between, so we're going to just do the mechanics of the cross product like we just did. We know that we're going to get a three-dimensional vector. And the way we can do it, if you stack your vectors like this, you don't even have to write that determinant down. You can cross out the first column, and you're going to get 0 minus 0. Cross out the second column, and you're going to get negative 50 plus 5, which is negative 45, and change the sign. And then the third, you get 0 minus 0, so you get that. So this tells us that the cross product is in which direction? In the y direction, because there's no x or z component, so it's only in the y direction. And what would the torque be? The torque is the absolute value or the magnitude of that vector.
45?
45 newton meters if they have standard units, which they don't mention up here, but we'll assume it's standard units for the torque. Does that make sense?
How does it change if, say, like those two aren't 0 though?
Well, then it would be going in an off-axis direction. So this is simple enough that we can say that it's in the y direction. Yeah, hopefully they don't give us one that's in the off-axis direction. Yeah. All right, so let's go look at one more of these, and we'll jump to our last section. Uh-oh, a bike. Yikes. So, set of brakes exerts a force on the rim of the wheel. It creates a force of 40 newtons perpendicular to the radius of the wheel. Assume that the wheel has a radius of 66 centimeters. Warning, that's not meters. Find the magnitude and direction of the torque about the axle of the wheel. So let's write down our two vectors. We're going to put R first. R is pointing up. If we imagine this in a three-dimensional coordinate system, that would, I guess, be the z direction. We'll imagine x coming out of the board, maybe. So we'll call that z direction. R is how big? 0.66 meters. So I would represent that this way if we do what I just said and use z up, y to the right, and x out. Doesn't matter which way we choose,
So then
really.
it's going like this, out.
Yeah, so this would be going from R to F.
Oh.
That would be going, because the application of the force is right there, and when we do position them like that, we get a different answer, but that's not how it works, because the vector has to be, this attachment point is right there. The force is being applied right there, so it's R, we're crossing R to F, so it's going to be into the board. So it's going to be in the negative x direction, the way I labeled the out direction.
Okay.
So we come up R and we're rolling to F. Think about that sushi roll.
So does that solve the problem we were talking about before then if we have to do tip to tail? We were talking about if it's on the opposite side, then it's negative, but you can't do
Yeah,
that.
but
if
when
it's
we're
on
doing
the-
torque, it's always applied at the tip of the
Always has
vector.
to
You
be
can't do it like
So
this.
you have to.
Yeah, if you apply both forces at the head of the bolt, that's not going to do anything.
Because that's the radius force.
So then the force is in the y
So
direction?
then the force is going to be in the y direction. Nico?
Rolling based on
What's that arrow within the wheel supposed to be?
This one?
Yeah.
That's the direction of the wheel.
Oh, see, he's going back.
So, well,
Well, think about
what's all this directional thing? Is he going backwards or forwards? So the wheel turns this way, and then the braking applies in the opposite direction. Okay. We need a bike.
No, I feel it.
We can't finish this problem without a bike. Okay, so then 0, 40, 0. Then we just cross those two together.
Okay, wait. That's the Y coming.
Trust me.
Yeah, that's what I'm stuck on right now. I think.
So the x component here is going to be
Y is coming.
0.66 times 40.
That's where the force
The
is.
y component is going to be 0. The z component is going to be 0.
You're looking for 26.4, by the way.
Thank you. Okay, so the cross product, that's interesting.
Shouldn't that be negative?
Yeah, oh, we didn't change the sign.
Yeah.
Oh, that sign doesn't get changed. The middle one's the one that gets changed.
So it's fine.
So that one's fine. So the x component, oh, but it is, we did forget about it. We don't change the sign, it just is negative because of the way we do our multiplication. Okay, and that matches what we expected. When we roll our fingers from R to F, it should point into the board, and the way we defined x to be out of the board, the negative direction is into the board. So our torque is 26.4 Newton meters.
Because you do this minus.
Yeah.
Main diagonal minus other diagonal.
0 minus that.
Does everybody follow that? So when we do the I component, we cross that out. Main diagonal is 0, other diagonal. So we get a negative.
So what do we say for the direction?
Am I right? Let it-
So the direction is going to be into the board. So in the negative x direction. So for us physically, it's into the board, but the way we defined everything, this would be the negative x direction. Now, if we defined our x, y, and z differently, it might be, depending on how, it might be a little bit. Yeah.
So depending on how we define our axes, would that yield a different answer? Say we had made, this is just x and y, since we're looking at a flat plane there, made R the y-axis, made F along the x-axis. Would this have yielded a different result? Or should it still
Well, let's find out. So if we did it this way, and we went, so if we did z in and out of the board, we would have to go from x to y, so the positive z-axis would be out, right? So if we went from, so x and y as coordinate system would have a positive z out, so then we would just label these a little bit differently, and it might be a little different.
You already lost me. Why do you have to go from x to y then? If you're going from R to F, so why don't you go?
But if we want to know which direction z is, if we're going to define this as positive x,
Right.
and this as positive y, isn't z straight out?
Based on what you told me before, no.
Yes, it is.
You're doing
No, forget about R and F. We're talking about x and y. If you're
Oh, so
creating,
now you're curling.
if you're creating your coordinate system's different than R and F. Forget about R and F. If we say this direction is going to be positive x and this direction is going to be positive y, positive z is going to be out of the board because from x to y is pointing out. So that's just our coordinate system. Now we look within our coordinate system, and we see that R and F, that's going to go in. That's going to go in the negative z direction.
Now I'm with you.
Okay. So it will be negative z direction instead of negative x direction.
Okay. But that shouldn't change our
But it's-
answer, though, right?
No, it's still going to be into the board at 26.4. Yeah.
Okay. Now we're on the same page. Then.
Oh, good. So important. Let's go to a new page. All right, so let's talk about functions. Functions! Functions. Have fun with the kid. Don't scare her with torque.
She likes bike wheels though.
She likes bike wheels. Ask her what direction you take off the... All right. Yeah, it'd be pretty bad if it was righty-tighty on both pedals. You'd end up with only one pedal. Okay, so we're going to talk about vector-valued functions in 14.5. So a vector-valued function in general is a function whose result, or its output, is a function as opposed to a real-valued function. All through algebra and Calc 1 and Calc 2, you were dealing with real-valued functions. You put in a number, you get out a number. So you're getting out a real number, so they call it real-valued. Here we call it vector-valued. We put in a number, that number is represented by t, and we're getting out a vector. We're getting out a, in this case, 3-component vector, so it's a vector-valued function. And that letter t is usually referred to as the parameter, and they use t quite frequently because of applications that involve time, so think of t for time. And then this r function is measuring your location at time t. So as t changes, you're at a different location. And typically what we think of when we're graphing a vector-valued function, we think about the trace that the tip of the vector is making. That's going to trace out a curve. So if this is t equals 0, we get a point. We just get the tip of the vector. So this curve is the collection of all vector tips. So as that vector-valued function changes, as time changes, we get new vectors, we get new terminal points, and the collection of all terminal points is the graph of the function. All right, so that makes sense? I mean, pretty abstract so far. We're just thinking about a function. We plug in different t values, we get different vectors, and then if you connected all the endpoints, you would get a curve. Okay, not a surface, a curve, because there's only one parameter. We'll see that if we want to have a surface in 3-dimensional space, we would have to have 2 parameters. But if we just have one parameter, we're getting a curve in 3-dimensional space.
Yeah, when graphing these vector functions, do we usually just set, do we just set the tail to the origins to kind of avoid confusion about where
The location?
Yeah.
So when we're graphing a vector value function, that's a good point, because there's an infinite number of representations for any vector. So when we're thinking specifically about the graph of a vector valued function, we're always positioning those R vectors from the origin. Yes, because that would be crazy if we weren't. It'd be hard to grapple with. So we talked a little bit about this last week, a line in 3-dimensional space. We need 2 things. So we have our line in 3-dimensional space. We're going to create a little formula that looks a lot like the slope-intercept form of a line. So the r0 vector, that vector is a lot like the y-intercept. That's telling us where we're going to start. So this is going to be our starting point right there. And then the vector v, which is right there, that vector v is a lot like slope. Right? Slope gives you your pitch. It tells you which direction you're going from the y-axis. If you pinpoint the y-intercept on a line, then your slope is going to tell you your pitch. It's going to tell you which direction you go. And that's what vector v is going to be. Now the more complicated thing is that we're in 3-dimensional space, so we've got this vector r0 in 3-dimensional space. It just touches our line, and then from that point where it touches our line, we have a direction that we're going. So that v vector is going to tell us the direction of the line. And then what we do is scale v by t to get all possible combinations in the v direction, negative and positive, to get all those dots. Every t value is going to correspond to one dot. When t equals 0, we're going to be at that dot. When t equals 1, we're going to be at that dot. When t equals 2, we're going to be at that dot right there. When t equals 3, we'll be there. 4. When t is 0.5, we'll be right there. So as t changes, we scale v. So when t is 1, we're going to go this direction 1v to that point. When t is 1/2, we're going to go 1/2 v to that point. So if you let t be any real number, You've got your R naught, and then you've got your V, and if you let T be any real number, you're going to scale V in both directions, all possibilities. That's going to give you all the dots on that line. And we're just using the triangle rule here to add. So if we add R naught and 1V, we would get that dot. Triangle rule. If we were adding R naught and half V, we would have a resultant vector that came up right here and gave us that dot. So T is scaling V, and then we keep adding R naught to it. So R naught plus 0.1 V, R naught plus 0.2 V, R naught plus 0.3 V. So T can be any real number. And that'll give us the entire line. So this is the equation of a line in 3-dimensional space or 2-dimensional space. It works for 2D also. Doesn't matter. So a line is a vector valued function, does not have a Cartesian equation as we talked about last week.
It's like y equals mx plus b.
Just like y equals mx plus b, except they write it sort of b equals xm.
Yeah.
So
Little backwards.
the R naught is the starting point, and then we have our scaling of vector v. So let's do one of those. So let's find the line. Maybe before we do that, no, let's just do it. We're good. All right. So you're imagining your coordinate system, and it doesn't, we're not going to draw this to scale. We're just imagining a coordinate system, and then we've got a couple of points. You know, we're just imagining these points, and I'm going to call this one 1, 0, 1, not to scale, not to scale. Don't try to think of this as to scale. All we need is a relationship between these points to try to get how the terminology fits in. So this first vector here, this is R naught. Is that the only option for R naught? No. You could have chose that one. Does not matter. For a vector valued representation of a line, there's an infinite number of choices. There's an infinite number of R naughts. There's an infinite number of V's. So I'm going to choose that one to be R naught. So R naught is, as a vector, will be the vector 1, 0, 1, because I'm displacing off of the origin to generate that vector. Now the vector v is the direction vector for the line. The direction vector for the line, it's like the slope. It tells you the pitch. It tells you what direction to go in, either in that direction or the opposite direction. So that's our vector v. That tells us the direction to head. So vector v we find by displacing this point minus this point. So we do that point minus that point, tip minus tail. So 3 minus 1, negative 3 minus 0, 3 minus 1. So that's our direction vector. That's like slope. It's telling us which direction to go. So if we add those two together, don't we just get a single vector? If we add those two together, we are going to get the vector right there. Do you agree that this dotted vector is R naught plus V? Agree? And that's just giving us 1 point. So this is the triangle rule. When we line up two vectors this way, if we wanted to, we could take that vector and we could put it down here, oops, and use the parallelogram rule. It doesn't matter, whichever your favorite method of addition is. If you put it right there, the diagonal would be formed, and that would work totally fine. Right there. Oh, dang it. Why did that happen? I don't know. That. So you could use the triangle rule or the parallelogram rule. It doesn't matter. But this is just one dot. That's it. If we want all the dots on that line, we need to scale v. We need to create a whole function. So we're going to say R of t is going to be R naught, not just plus v, we need to scale it. We want to get all of the possible points that are scalar multiples of v. V. So if we let t be 1/2, we would be getting that point right there. So this is going to correspond to t equals 0. This is going to correspond to t equals 1/2. That's going to correspond to t equals 1. So all the points on the line are generated by unique values of t. Every value of t, 1 point on the line. Every point on the line corresponds to 1 value of t. So when we finish off this vector valued function, we want to compress it and write it as a single vector. So it's going to be 1 plus 2t, comma, negative 3t, comma, 1 plus 2t. So there is our vector valued function where t is a real number. T is an element of the reals. So that right there is the equation of the line that we're looking for. So starting point plus a scaling of our direction. When we add all possibilities, we get the entire line. So the line that we're getting then is this whole line through V. Right? We're going to get that whole line. These points on the line are going to happen when t is -1, -2, -3. We're going to get the other half of the line. So the R0 acts like the origin of the line. All right, let's try this.
Question?
Yeah, go for it.
So, what were to happen if you were to parameterize R with something that's not linear, like t squared or something? Would you get like a curve in 3D space or no?
You would just not have uniform steps. So if you want, so the way we're parameterizing this line, we're parameterizing in a way that each value of t is corresponding to the same distance between consecutive integer values of t. But if your line had some other stuff in here, if you had a t squared there and did it another way, t squared might not be a great selection because that would force the coordinate to always be positive. But you can choose a non-linear representation still of a line. It's just that the points might be plotted faster. You know, like if you graph it on a graphing utility, you can see the speed at which points are plotted. When you do it linearly, 1 point, 1 point, 1 point, the points can get compressed if you use a non-linear function. You're still graphing the same line, but it's just that they're plotted slightly differently. You know, if this is t equals 1 and this is t equals 2, t equals 3 might be right next to t equals 2 instead of the same distance from where t equals between t equals 1 and 2. So yeah, definitely possible though to still have a line when those aren't linear. If you have those being linear, you're most likely getting an infinite line. You are getting a line that goes off in both directions. You might get half lines and things like that with what you're talking about. It's possible. We'll get into a lot more of that as we're going on. So the line through this point that's perpendicular to the z-axis and that vector. Okay, so right away they tell us that we have a point that's on the line for sure. That acts like our R0. So we're going to let R0 be the vector that points from the origin out to that point. So there's R0. We know that's on the line. That's going to act like the origin for the line. The other thing we need is a direction vector. So the direction vector is not given, but we can find it. So they tell us that the direction vector is perpendicular to two vectors. So if it's perpendicular to two vectors, what are we going to do? Find the cross product. If we find the cross product of those two, we will create a vector v that can act as our direction vector. There's an infinite number of them. You could do u cross the z-axis. You could do the z-axis cross u. There's all sorts of ways that you could come up with different v's that will all be parallel and equally valid. So can somebody give me a vector that points in the z direction?
0, 0, 1.
Oh, that's a great vector. Excellent choice. And so when we cross these two together, we're going to get this as our direction vector, whatever we get when we cross this. So first, write the structure of the vector down. And cross out the first column. We're going to have 3 minus 0. And then we're going to have 4 minus 0. Change the sign. And then cross out the z, and we get 0. So we're going to use that as our direction vector. You could use any scalar multiple of that, and it would also work. For example, if we happen to get, let's just say we got 10, 10, 2, we could divide it all by 2 and use 5, 5, 1. Totally fine. That's still pointing in the same direction. Right? T equals 5 would correspond to a different point on the line if you had a different direction vector, but you could use any direction vector that's a scalar multiple of the one you find. So if you ended up with 100, 100, 100, just use 1, 1, 1. So you can always scale. If direction is the only thing that matters, you can scale it all the way down to where there's no fractions, no common multiples. It doesn't matter as long as it has the same direction or opposite direction, as long as it's parallel. So if it was negative, 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 you can multiply by -1 and choose positive, positive, positive just to simplify your answer. So that makes it hard to grade because there's a ton of answers that are all right. So R of t is going to be R naught plus TV. R naught plus TV.
Maybe you could have us all just use unit vectors for V.
Yeah, you could do that too.
And
That'd be a little messy at times, but I could do that.
Yeah, make
Not a
the
bad
list
idea.
grade. Yeah, specific origin point and use unit vectors.
Yeah, have to use unit vectors. So that is our line right there. Just notice when you plug in, let's plug in some t values. Just notice this is, make sure you're thinking of this correctly. Plug in t equals 0, you get 3, you get 0, 2, 1, which is what you would expect to get. That's the R naught, 0, 2, 1. It corresponds to the origin of the line. Plug in t equals 1. When you plug in t equals 1, you better get back to V. When you plug in t equals 1, you get 3, -2. What do I get? 3,
-2 and 1.
-2, 1. What did I say? 3, -2. Oh, I said you should get back to V. You shouldn't get back to V. Never mind. You won't get back to V. When you plug in 2, you're going to get 6, comma, -6, comma 1. You know, so every value of t is just giving you another point on the line. Yeah. All right, so this is the equation of our line. Every value of t, different point on the line. Any questions on that before we? So what about a line segment? What about a line segment? A line segment is just part of a line. So all we do is find the equation of the line and then restrict the domain. So let's watch this. So for R naught, what do you want to use? 101, great choice. There's only one other choice that would work easily, and that would be 0, -2, 1, would be totally fine. Vector V is our direction. We'll just go right minus left just to be consistent with what we've been doing. Doesn't matter though, you could go the other way. You could do 1, 0, 1 minus the other point would totally work. So here, if you wanted to, you could also say, oh, well, 1, 2, 0, that would work. If you just scaled it by a factor of -1, totally work. Doesn't matter. All those are good choices. So I'm going to choose these two, though, just because I selected them to begin with. So R of t is going to be R naught plus TV. So if I wrote this out, this is going to be t, 1 minus t, 1 minus t, comma, -2t, comma, 0 plus 1, so 1. So that's going to be the entire line. That's going to be the entire line. I'm not using that one. I'll just put an X over there. That's going to be the entire line if you let t be a real number. What do you think we want to restrict t to so that we get just the line segment?
From 0 to 1.
0 to 1. Let's check. When you plug in t equals 0, you get 1, 0, 1. When you plug in t equals 1, you get 0, -2, 1. That's kind of what was in my mind last time when I said if you plugged in 1, you would get V, but that's not how it works. When you plug in 1, you get the terminal point of your direction vector. So that restriction is all we have to do. And that restriction will always give you a line segment from point P to point Q if you don't scale V. If you use the V that you found, T 0 to 1 will always be the correct numbers to pick. If you divided V by 2, what do you think your T interval would be?
0 to 1/2.
Other way, 0 to 2.
0 to 2.
0 to 2.
Multiply.
Yeah. If you scaled your V down by 1/3, you'd have to multiply your interval and go 0 to 3. You can always test. Plug in 0, make sure you're at that point, and then just plug in 1, plug in 2, plug in 3, make sure you're at the terminal point.
Oh, I think I get it. So is it just one's like normalized, meaning entire length,
Mm-hmm.
and then half length? Okay, that makes sense.
Yeah. Yeah, so if your V, if the V between these 2 points had a common factor of 5, and you divided out the 5, so maybe it was 5, 10, 15, you divided out the 5, so you had 1, 2, 3, then to get to the terminal point, you would have to adjust there and go from 0 to 5, because you scaled your direction vector down by 5, so now you need to let your time interval increase by 5 so that you get all the way back to the original endpoint. This will be part of the project that we do too. We'll see this type of domain manipulation soon. So let's see what we get here. The obvious choice is to use 248 for R0. That we cannot change because that vector goes out and touches our line. So if we scaled R0 back, we'd be moving the whole line. So R sub 0 points out and touches the line. We can't scale that. So R0 has to touch the line. The vector that we can scale is V. V is a vector that points, when it's only direction that we care about, it doesn't matter how long that vector is. So now let's figure out the natural choice for V would be that minus that. So 5, 1, negative 5. And then our natural way to create R would be R0 plus TV. Combine our corresponding components. And when we combine our corresponding components, we'll end up with this vector value function. And that gives us the entire line through those 2 points. We want to say, hey, we don't want the whole line, we just want part of the line.
0 to 1?
0 to 1. And check. If you plug in 0, you get 248. And if you plug in 1, you get 7, 5, 3. So, vector value function. Question?
So if you use that first point as your as the vector for the R0, will it always be restricted from 0 to some other number? Like it always starts at 0?
Yep. Yep, exactly. It's always going to be, and it's always going to be 0 to 1 if your V is terminal point minus initial point.
Okay.
So if you don't scale that vector at all, that's always going to be 0 to 1 for a line segment, no matter what. Before we do that, let's notice, and you're ready, Okay, let's go to limits. All right, let's go to limits.
Doesn't exist.
It doesn't exist. D and
I
E.
don't like it.
I was going to try to delay, but then I saw the time. We cannot delay. You're ready. The cool thing about Calc 3 is that it's just Calc 1 3 times. That's it.
Everyone in the class
It's just 3 problems compressed into 1. It's like part A, B, and C. Right? So when you take the limit, the nice thing, so first off, I would write this slightly differently. Us math people would prefer to write it like this, so that it's totally obvious that you're dealing with a vector, and the I, J, and K don't potentially lead to something goofy. So the limit of a vector valued function, all we do is take the limit of each component. So it's literally Calc 1 3 times. Now, I would never write this step down, and I will never write it down again. But this is what it means. You can take the limit symbol and you can jump it across to each component. So the limit symbol is something that distributes to each component. And so if you want to figure out the limit of a vector valued function, you do the limit of the first component, limit of the second component, limit of the third component.
And that's your vector.
And that's going to give us a vector.
Okay.
So the limit of a vector valued function is another vector. Right. Just like the limit of a real valued function is a scalar. And so then we all know, okay, when we have a function that's continuous, all you need to do is plug in the limit down there, plug it in up there, and we're going to get e to the ln of 2, which is 2, so we're going to get a 4. For this middle one, can you do that in your head?
-12.
Nope. Guess you can't.
I couldn't
So-
do my head, Mike.
I'm like,
So we're
letters are
6
so-
e
That
to
was
the
like the other
negative
option.
ln2.
Yeah.
So before you can collapse your exponential and log, that negative has to pop up here and get out of the way so that those collapse. So you're going to have 6e to the ln of 1/2. Because that 1 comes up on the 2 as a reciprocal, we'll get that to be 1/2. Those collapse, so we get 6 times 1/2, which is 3. So that'll be our middle component.
I looked at this the first time, I was like, oh no. I can't
What was
remember.
that?
I literally can't.
No,
This
yeah, not
next
for
one's-
limits.
okay,
Yeah,
so it's
just
negative
cross
4.
product.
Okay, sorry.
Oh, that's fine.
So it's just 1.
So for this one here, we plug in the ln2 up there. That negative 2 has to be moved up to an exponent position on the 2. 2 to the negative 2 is 1/4. So we're going to get 1/4 times negative 4. So we're going to end up with negative 1.
Let's try that out.
I'm still doing limits.
Yes, so refresher. And now we get to do a refresher on
The hospital.
the hospital rule.
Oh,
Okay, so any questions on the above one before we go to L'Hopital's rule? So L'Hopital's rule is a rule that works when you're trying to find the limit of a fraction and you end up with an indeterminate form like 0 divided by 0 or infinity divided by infinity. So L'Hopital's rule works whenever that's the case. L'Hopital's rule says the quotient of two functions is the same as the quotient of two derivatives. In your mind, for derivatives, you're thinking tangent lines. And so conceptually, it should make sense. If you're looking at the quotient of two functions, and the best approximation for a function is a derivative, the quotient of derivatives should give you the same answer. So a quotient of two functions, the quotient of two derivatives should give you the same answer. So when we look here, plugging in 0, tan 0 is 0. So we get 0 divided by 0, so that is indeterminate, so we're going to use L'Hopital's rule there. Let's go with that one first, and then we'll talk about the sine one. So this is going to be, so this is going to be the limit as t goes to 0. Bless you. What's the derivative of tan squared? Excuse me, derivative of tan. Sec squared. The derivative of tangent is sec squared.
Tan squared.
Derivative of tangent is sec squared of t. The derivative of t is just 1. So that. Now, when we plug in t equals 0 here, we get 0 divided by 0 again, so we can use L'Hopital's rule. The derivative of the numerator is 3. The derivative of the denominator is cosine of t. How about the last one? Is there any funny business?
No.
Nah.
There is.
No funny business. No funny business. All right, so now we're good to go. So now secant of 0. Secant is the reciprocal of cosine. Cosine of 0 is 1. The reciprocal of 1 is 1. 1 squared is 1. 1. So we get 1. Cosine of 0 is 1. So we end up with -3. With a square root function, that's a continuous function, so you can push the limit inside the square root function. The limit of t plus 1 is just 1. So that's going to be the square root of 1, which is 1. So that's our limiting vector. Limiting vector. Any questions on that? All right, so let's do the harder ones. They're not that much harder. All right, point of intersection. So both of those are lines. They're both given to us as vector-valued functions. And the question says, determine an equation of the line that is perpendicular to those lines and passes through the point of intersection. So we've got two lines in three-dimensional space. They claim that they intersect. We'll find out in a second, make sure that they do intersect. And we want the equation of the line that goes through that intersection point perpendicular to both those lines.
Cross product.
So we're going to use the cross product to get the direction of the new line. And we're going to use a system of equations to figure out where those two meet. Right? We've got to use some sort of system to find out where two objects intersect. So let's go ahead and figure out where they intersect first. So these two lines, if we want to figure out where they intersect, we're going to set the x component equal to the x component kind of thing. So we have -2 plus 3t equals -6 plus s. We have to use a different parameter. We're using s for one and t for one. We can't use the same letter for both. Just because they intersect doesn't mean they intersect at the same time. Does that make sense? Here, watch. So as we do this, so as we set these equal to each other, like, watch and see what happens.
3t.
All right. So,
You went 3, 2, 3. I did that.
say again?
You
Yeah,
went
you went
3, 2, 3 on the t's. Coefficient of t's.
Oh.
You change your coefficient of 1.
So we're setting these equal.
Oh.
Those equal.
Okay.
to
I thought you were solving for
the
someone else.
mystery.
I thought you, yeah.
Yeah, so we're setting x equal to x, y equal to y, z equal to z. So we've got these we've got these two lines with three components. So we're going to set the corresponding components equal and try to figure out if there's a relationship between s and t. So we have to use a system here. Let's take a look at first equation, third equation, and take the difference. If we take first equation minus third equation, we get -2 equals +6, -2s. Did I subtract properly? And that tells me that s is equal to 4. Everybody agree with that? So I did top equation minus bottom equation. -2 minus 0 is -2. 3t minus 3t is 0. -6 minus -12 is -6 plus 12, which is 6. S minus 3s is -2s. Solve for s. So that tells us that the intersection point occurs when s is 4. So that intersection point, if we plug in s equals 4 up into that equation, plug in s equals 4, that gives us the ordered triple, -2, 0, 0, -2, 0, 0.
Nice.
Now, if we don't trust ourselves with arithmetic, let's make sure that that's the same point that is on this line for a different t value. So let's check. When s is equal to 4, that tells me that t is equal to, if I come in here, if s is equal to 4, t is equal to 0. Let's check then. If we plug 0 into the t equation, do we get the same ordered triple? Plug in t equals, oh yes, we get the same ordered triple. So we did it right. So that is the intersection point, -2, 0, 0.
First time today.
So that's going to be the intersection point. So when we build our line, we're going to have -2, 0, 0 as our displacement, as our vector here, plus t times, we need a direction vector now. And how are we going to find that direction vector? Taryn, you said it earlier. If we're going to be perpendicular to both of those guys, we're going to take the direction of line 1, the direction of line 2, and cross them. So let's come over to the side and do that. So the direction of line 1 is 3, 2, 3. The direction of line 2 is 1, 2, 3. So this is line 1, this is line 2.
Where did you get
Those are the coefficients of t. The direction vector is always the coefficients of t. So when we have a line, r sub 0 plus tv, the coefficients of t are forming that direction vector. We'll do a couple more of these next time. I'll just finish this one off because we don't have much time. So I'm going to cross these to get the direction vector of our new line. And that's going to give us 6 minus 6, which is 0. It's going to give us 3 minus 9, which is negative 6. And it's going to give us 6 minus 2, which is 4. So that is going to be our direction vector, 0, negative 6, 4.
Did you change the sign on the 6?
I think I did.
You did, yeah.
So that would be a representation of our line. Okay, so we have a minute for questions.
How do we get t equals 0 from s equals 4?
So the way that I got t equals 0 from s equals 4, I simultaneously solved these two equations, correct? And so whenever you have a system with two equations and two unknowns, you find one and plug it back into either to get the other. So plug in s equals 4 here, or plug in s equals 4 here. And that will give you the corresponding t value. So this tells us that time is 0 on this line and time is 4 on this line when they intersect. Like if you send two missiles into the air, right, they're not going to intersect at the same t value. If one missile's coming from, I don't know, Russia, and one's coming from the United States, those are going to be different t values, right?
They're going to take off at different times.
So the intersection, just because they intersect doesn't mean they intersect at the same value of the parameter. And then once we get that, then we look at the coefficients of the parameter to get the direction for each line. Cross those and we're good to go. Eric?
I'll have to read the books. I'm trying to figure. I'm still figuring out how you got 3, 2, 3.
Okay, so yeah, let me explain that. So when you look right here, the coefficients of t, those are those. So the direction of a line is always going to be found by looking at the coefficients in front of the variable. So the 3, 2, 3 is coming from the coefficients of t for each component. And if you look at the coefficients of s are 1, 2, 3. Those are where those are coming from. Ooh, bad letter, bad color choice. I don't know what's a better color choice. I think I'll just go like this, purple. So underline that, and that. Those are this, and this. So the coefficients of t, coefficients of s. And then if we cross them, that's going to give us the direction of the line that's going through that point of intersection. Other questions for anyone? Omar?
Oh, that makes sense now. I was wondering how the hell you pulled that out of freaking nowhere.
3, 2, 3. 1, 2, 3.
Yeah, I was like, wait, what?
There's a lot of numbers up here. Set this equal to that, but not that equal to this, and then take the coefficients of the t, but not the s, and then the coefficients of s, but not the t. Yeah. Some voodoo. Other questions on that?
I have to get out of here, but
Yeah.
I wanted to stay for office hours, but so
No problem.
I'm gonna grab my pen now.
Which one is it? The red one?
one.
Red. Michael. Say that once again.
How are you getting the equation for s equals 4?
How am I getting this right here?
Yeah.
Okay, so when we have a system, we can either use elimination or substitution.
Correct.
And so what I did was subtracted. So this is equation 1 minus equation 3 right here. So this is equation 1 minus equation 3. So this one we're calling equation 1, this one's going to be equation 2, and this one's going to be equation 3.
Okay.
So if we subtract equation 1 minus equation 3, this is a 0 plus 3t, so negative 2 minus 0, 3t minus 3t, negative 6 minus 12, s minus 3s. And so that gives us this, which is a linear equation. We solve it for s. And we can plug that s value back into either of those equations to get the corresponding t.
Okay, that makes sense.
And then any value of s or any value of t is going to correspond to a point on the respective line. So if we plug s equals 4 into the s equation up here, the s line gives us this point. And if we plug t equals 0 into the t line, they better correspond to the same point if they're truly intersecting at that value of the parameter.
And t equals 0 is just because we don't have a t there, so if there's no t.
So t equals 0, so because s is 4, then we come up here and we say, oh, what is t when s is 4? So if we come and we do negative 2 plus 3t equals negative 6 plus 4. So that turns into negative 2. The negative 2's cancel. We get 3t equals 0. We get t equals 0. So the t equals 0 is coming from the value, the other value in this system of two equations. So when s is 4, that corresponds to the same point on the s line as t equals 0 corresponds to on the t line. And we didn't have to go through this if we're totally confident that we solved this correctly. We know that's the point of intersection. We could just go. But just to make sure, we went with the check method.
You solve for t and do it the other way?
Yep, absolutely. So if we wanted to solve for t first, like for example, if we multiplied this equation by negative 2, we could add them and the s's would disappear and we would solve for t. And we get t equals 0 and then that would correspond to t equals 4, s equals 4.